What if I told you that everything you see, the stars, the planets, even the vast expanse of the night sky, is just the tip of the cosmic iceberg? Beneath the surface of what we can observe lies a universe that is 95% invisible, made up of dark matter and dark energy, forces so mysterious that they challenge everything we think we know about reality. This hidden cosmos doesn't just defy our understanding, it invites us to rethink the very nature of existence. What lies beyond the limits of our perception? How do these unseen realms redefine our place in the universe? These are the questions that will guide us as we journey into the hidden depths of the cosmos, exploring cutting-edge theories, unraveling cosmic secrets, and discovering perspectives that will expand your mind in ways you never thought possible. This is not just a story about science, it's a journey into the profound, the unknown, and the awe-inspiring. Are you ready to see the universe in a whole new light? Let's begin. It's easy to look up at the night sky and feel a sense of awe at its grandeur, but here's something that might stop you in your tracks. What we see, all those glittering stars and swirling galaxies, makes up just 5% of the universe. The rest, it's hidden, cloaked in shadows so profound that even our most advanced tools can't fully pierce them. This is the illusion of the observable universe, a sliver of reality, a fraction of existence, while the vast majority remains beyond our reach. Think of it like standing in a dimly lit room holding a flashlight. The beam illuminates a small circle of space, revealing a few objects, but the rest of the room, its true size, its secret, stays in darkness. That's humanity's relationship with the cosmos. Our telescopes, no matter how powerful, are like that flashlight, limited by the speed of light and the age of the universe. We're peering through a keyhole into an infinite room, catching glimpses of what lies beyond, but never the full picture. This cosmic horizon isn't just a boundary, it's a reminder of how much we don't know. It's humbling to realize that everything we've ever observed, every star, every planet, every galaxy, is just the surface of something far more immense. And yet, this limitation doesn't mean we're powerless. It challenges us to push further, to ask deeper questions, and to imagine what might lie beyond the edge of what we can see. The unseen parts of the universe aren't empty or inert, they're alive with forces we're only beginning to understand. Dark matter, an invisible scaffolding that holds galaxies together, and dark energy, a mysterious force driving the universe to expand faster and faster, are the hidden architects of reality. They shape the cosmos in ways we can't directly observe, yet their influence is everywhere, from the smallest particles to the largest structures in existence. So, what does it mean to live in a universe where most of what exists is invisible to us? It's a question that doesn't just challenge science, it challenges our very perception of reality. As we begin to unravel the secrets of the unseen cosmos, we're not just exploring space, we're redefining what it means to see, to know, and to exist within this vast, mysterious universe. Imagine a force so pervasive, so powerful, yet so elusive that it shapes the very fabric of the cosmos, and yet we've never seen it. This is dark matter, the invisible architect of the universe, making up a staggering 27% of everything that exists. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light. It's completely invisible, and yet its presence is undeniable. How? Because it leaves a trail of gravitational breadcrumbs, clues that scientists have been piecing together for decades. The story of dark matter began with a puzzle. In the 1930s, astronomer Fritz Zwicky noticed something strange about galaxies in clusters. They were moving too fast, so fast that the gravity from their visible stars and gas couldn't possibly hold them together. It was as if an unseen force was at work, tugging at the edges of reality. Decades later, Vera Rubin's groundbreaking work on galaxy rotation curves confirmed it. Stars on the outer edges of galaxies were orbiting just as quickly as those near the center, defying the laws of gravity as we understood them. The only explanation, a vast halo of invisible matter wrapping around galaxies like an unseen hand guiding their motion. This invisible hand doesn't just hold galaxies together, it shapes the universe on the grandest scales. Dark matter is the cosmic glue that forms the scaffolding of the universe, the backbone of the so-called cosmic web. Picture a spider's silk, delicate yet strong, stretching across the void. Galaxies and clusters form at the intersections of these threads, drawn together by the gravitational pull of dark matter. Without it, the universe as we know it wouldn't exist. But what is dark matter? That's the question driving some of the most ambitious experiments in science today. From deep underground detectors searching for elusive particles to massive colliders smashing atoms in hopes of uncovering its secrets, the hunt is on. Astrophysicists have proposed countless theories. Perhaps dark matter is made of weakly interacting massive particles, or WIMP, or maybe it's something even stranger like actions or sterile neutrinos. The truth is, we still don't know, but every failed experiment, every null result brings us closer to understanding this enigmatic force. Dark matter's invisibility doesn't make it any less real. It's a reminder that the universe is far more complex than what meets the eye. And if dark matter challenges our understanding of the cosmos, its counterpart, dark energy, takes that challenge to an entirely new level. But that's a mystery for another moment. For now, let's sit with the awe-inspiring idea that most of the universe's mass is hidden, a silent force shaping everything we see and everything we don't. If dark matter is the invisible hand shaping the structure of the universe, then dark energy is the breath that propels it forward, pushing galaxies apart at an ever-increasing speed. Discovered in the late 1990s, dark energy is perhaps the most baffling force in the cosmos, a mysterious energy that permeates all of space and drives the accelerated expansion of the universe. It's like a cosmic wind, invisible but relentless, stretching the fabric of reality itself. The discovery of dark energy came as a shock to scientists. By studying distant supernovae, researchers found that these exploding stars were fainter than expected, indicating they were farther away than they should have been. The only explanation: the universe wasn't just expanding, it was speeding up. This revelation overturned decades of assumptions and introduced a new chapter in our understanding of the cosmos. So, what is dark energy? The truth is, we're still grappling with that question. One leading theory suggests it's a property of space itself, often referred to as vacuum energy or the cosmological constant. Imagine empty space not as a void but as a simmering sea of energy, constantly exerting a gentle yet unstoppable force. Another possibility is that our understanding of gravity is incomplete, that Einstein's theory of general relativity, while remarkably accurate, might need adjustments on the largest scales. Whatever its nature, dark energy makes up a staggering 68% of the universe, dwarfing even dark matter in its influence. The implications of dark energy are as profound as they are unsettling. If this acceleration continues, the universe could face a fate known as the Big Freeze, where galaxies drift so far apart that the cosmos becomes a cold, dark, and lonely place. But dark energy also raises a fascinating paradox. Despite its overwhelming dominance, it's almost impossible to detect directly. Unlike dark matter, which reveals itself through gravity, dark energy leaves no obvious fingerprints. It's a force that shapes the universe yet remains maddeningly elusive. This paradox invites us to consider the limits of human knowledge and the possibility that some truths about the cosmos might always lie beyond our grasp. But it also inspires wonder. If dark energy is pushing galaxies apart, what else might it be doing? Could it be connected to other mysteries like the birth of the universe or the existence of parallel realities? Speaking of parallel realities, dark energy opens the door to one of the most mind-bending ideas in modern physics, the multiverse. If the universe is expanding faster and faster, could there be other universes out there, each with its own laws of physics, its own version of reality? It's a concept that stretches the imagination, but it's one we'll explore as we dive deeper into the hidden realms of the cosmos. For now, let's sit with the astonishing idea that the universe isn't just expanding, it's racing into the unknown, driven by a force we can't see, barely understand, and are only beginning to unravel. What if our universe is just one thread in an infinite cosmic tapestry? This is the radical idea at the heart of the multiverse theory, a concept that suggests our universe might not be the only one, but instead one of countless others, each with its own unique laws of physics, history, and even versions of reality. It's a mind-bending idea that challenges everything we thought we knew about existence, and it's supported by some of the most cutting-edge theories in physics. One of the most compelling arguments for the multiverse comes from a concept called eternal inflation. Imagine the early universe as a rapidly expanding bubble, growing faster and faster. According to this theory, our universe is just one bubble among many, each forming within a vast, ever-expanding cosmic foam. Some bubbles might collapse, others might stabilize, and some could give birth to entirely new universes. It's a process that could be happening endlessly, creating an infinite number of realities. But the multiverse isn't limited to just one theory. String theory, one of the most ambitious attempts to unify all the forces of nature, suggests that our universe might exist within a landscape of possible realities. In this view, the fundamental constants of physics, like the strength of gravity or the mass of an electron, could vary from universe to universe, creating a staggering diversity of worlds. Some might be lifeless voids, while others could teem with life in forms we can't even imagine. Then there's the idea of quantum branching, which proposes that every possible outcome of every event actually happens, splitting reality into infinite parallel timelines. Did you turn left instead of right this morning? In another universe, you turned right. Did a historical event unfold differently? Somewhere out there, it did. This version of the multiverse suggests that every choice, every chance creates a new reality, leading to an almost unimaginable web of possibilities. These theories aren't just scientific curiosities, they force us to confront profound questions about the nature of reality. Are there infinite versions of ourselves out there, living lives we might have lived? Could there be universes where the laws of physics are so different that life as we know it is impossible? These ideas blur the line between science and philosophy, challenging us to rethink not just the cosmos but our place within it. Cosmologists are divided on the multiverse. Some see it as a natural extension of our current understanding of physics, while others argue it's untestable and therefore outside the realm of science. But whether or not we can ever prove the existence of other universes, the multiverse invites us to dream bigger, to imagine a cosmos far more vast and varied than we ever thought possible. As we push the boundaries of space and time, the multiverse reminds us that reality might be far stranger than we've dared to imagine. And if there are truly infinite universes out there, what does that mean for the one we call home? It's a question that doesn't just expand our understanding of the cosmos, it expands our sense of wonder. Now, let's turn our attention to one of the most extreme and fascinating phenomena in the cosmos, black holes. These cosmic whirlpools, where gravity becomes so intense that not even light can escape, are more than just celestial oddities. They're windows into the very fabric of space and time. Imagine a place where the rules of physics as we know them break down, where the universe folds in on itself, creating a point of infinite density known as a singularity. This is the heart of a black hole, a region so bizarre that it challenges our understanding of reality itself. Black holes form when massive stars, many times heavier than our Sun, exhaust their fuel and collapse under their own gravity. The star's outer layers explode in a spectacular supernova, while its core crushes down into an infinitely dense point. This creates an event horizon, a boundary beyond which nothing, not even light, can escape. Picture it as a cosmic point of no return, a one-way door into the unknown. The first image of a black hole, captured in 2019 by the Event Horizon Telescope, was a landmark moment in science. For the first time, we saw the shadow of a black hole's event horizon, surrounded by a glowing ring of superheated gas. This image wasn't just a scientific triumph, it was a glimpse into the extreme conditions at the edge of space-time. But black holes aren't just cosmic vacuum cleaners. They're also laboratories for testing some of the most profound questions in physics. Take the information paradox, for example. According to quantum mechanics, information can never be destroyed, yet black holes seem to defy this rule. When matter falls into a black hole, does the information it carries disappear forever? Stephen Hawking proposed a solution. Black holes might emit radiation, now known as Hawking radiation, slowly losing mass over time. This radiation could carry away information, preserving the laws of physics, but the details remain one of the greatest mysteries in science. Gravitational waves, ripples in space-time caused by violent cosmic events, have also given us new insights into black holes. In 2015, the LIGO Observatory detected waves from two black holes colliding, a discovery that confirmed Einstein's prediction of these waves and opened a new way to observe the universe. These collisions reveal the incredible power of black holes, capable of shaking the very fabric of reality. Black holes aren't just destructive forces, they're also gateways to new possibilities. One tantalizing idea is that they might connect to other regions of space and time through wormholes, hypothetical tunnels that could serve as cosmic shortcuts. While wormholes remain purely theoretical for now, they spark the imagination, offering a vision of a universe far more interconnected than we ever imagined. As we explore the mysteries of black holes, we're not just studying distant objects, we're probing the limits of space, time, and our own understanding. These cosmic enigmas remind us that the universe is stranger, more beautiful, and more mysterious than we can comprehend. And as we push the boundaries of knowledge, we're left with one irresistible question: what other secrets lie hidden in the depths of space-time? What if you could step through a doorway and emerge light years away, or even in a different time? This is the tantalizing promise of wormholes, theoretical tunnels through space-time that could act as cosmic shortcuts, connecting distant parts of the universe or even different moments in time. While they sound like something straight out of science fiction, wormholes are rooted in real science, emerging from the equations of Einstein's theory of general relativity. But are they truly possible, or just a fascinating mathematical quirk? The idea of wormholes dates back to 1935, when physicists Albert Einstein and Nathan Rosen proposed the concept of an Einstein-Rosen bridge, a theoretical connection between 2 points in space-time. Picture a sheet of paper representing the fabric of the universe. If you fold the paper so 2 points touch, a wormhole would be like poking a hole through the fold, creating a direct path between those points. It's a shortcut through the cosmic landscape, bypassing the vast distances that would otherwise separate them. But here's the catch: wormholes, as we understand them, are incredibly unstable. Without something to hold them open, they would collapse almost instantly. This is where exotic matter comes in, a hypothetical substance with negative energy that could theoretically counteract the immense gravitational forces trying to crush the wormhole shut. Exotic matter isn't something we've discovered yet, but its existence is allowed by the laws of physics, making it a key piece of the wormhole puzzle. The potential applications of wormholes are as mind-bending as the concept itself. Imagine using one to travel across the galaxy in an instant, or even stepping through a portal to a different point in time. These ideas have fueled countless stories in science fiction, but they also raise profound scientific questions. Could wormholes make interstellar travel feasible? Could they allow us to revisit the past or glimpse the future? Theoretical physicists have explored these possibilities, but the challenges are immense. One of the biggest hurdles is stability. Even if exotic matter exists, it's unclear whether it could sustain a wormhole long enough for anything or anyone to pass through. The energy requirements would also be staggering, potentially requiring more energy than the entire universe contains. And then there's the question of paradoxes. If time travel were possible through a wormhole, could it create contradictions like the famous grandfather paradox, where traveling back in time could alter events in ways that erase your own existence? Despite these challenges, wormholes remain a captivating area of study. They push the boundaries of what we think is possible, forcing us to confront the limits of our understanding. Some physicists believe that wormholes could be connected to quantum entanglement, where particles instantaneously affect each other across vast distances. Others suggest that wormholes might be too small to ever be traversable, existing on scales so tiny they're beyond our ability to detect. Whether wormholes are cosmic shortcuts or just a beautiful idea, they invite us to dream bigger and explore the furthest reaches of possibility. They remind us that the universe is full of wonders we've yet to uncover, and that the line between science and science fiction is often thinner than we think. As we ponder the nature of wormholes, we're also led to a deeper question. What is time itself? Is it a rigid structure or something more fluid, something we might one day bend to our will? This question takes us into the heart of one of the most profound mysteries of the cosmos, a mystery we'll explore next. What if time isn't what we think it is? We're taught to see it as a steady, unchanging river flowing from the past through the present and into the future. But what if this is just an illusion? Einstein's theory of relativity shattered the idea of time as a universal constant, revealing that it's far more fluid and far stranger than we ever imagined. According to relativity, time isn't absolute. It can stretch, contract, and even bend, depending on how fast you're moving or how strong gravity is around you. Take the famous twin paradox, for example. Imagine one twin stays on Earth while the other travels through space at near light speed. When the traveling twin returns, they'll find that less time has passed for them than for their sibling on Earth. It's not science fiction, it's a real consequence of time dilation, a phenomenon confirmed by countless experiments. Time, it turns out, is deeply personal, shaped by your perspective and your place in the universe. But relativity is just the beginning. Some physicists suggest that time might not even flow at all. Enter the block universe theory, which proposes that past, present, and future all exist simultaneously like frames in a film strip. In this view, time is a dimension just like space, and every moment from the Big Bang to the distant future is fixed in place. It's a radical idea that challenges our everyday experience, but it's one that aligns with the mathematics of relativity. This raises a profound question. Is time just a human construct? Our brains are wired to perceive time as a sequence of events, but what if that's just a survival mechanism, a way for us to make sense of the world? Philosophers have long debated this, with some arguing that time is a mental framework, not an objective reality. Even physicists like Carlo Rovelli suggest that time might emerge from deeper, timeless laws of the universe, appearing only when we zoom out to the level of human experience. These ideas aren't just abstract musings, they have real implications for how we understand the cosmos. If time is relative, what does that mean for the origins of the universe? Can we even speak of a beginning if time itself is part of the fabric of reality? These questions take us to the heart of one of the greatest mysteries in science, the birth of everything we know. As we explore the nature of time, we're not just unraveling the universe's secrets, we're redefining our place within it. And while the answers may be elusive, the journey itself is a testament to the boundless curiosity that drives us to look beyond the surface and into the depths of reality. So, what lies at the beginning of time? To answer that, we need to go back, way back, to the moment when the universe itself was born. But as we'll soon discover, even that moment is shrouded in mystery, waiting to be uncovered. Let's travel back, way back to the very beginning, to a moment when all of space, time, and matter were compressed into an infinitesimally small point. This is the Big Bang, the cosmic event that set the stage for everything we know today. It's not just a theory, it's the foundation of modern cosmology, supported by a mountain of evidence that paints a vivid picture of the universe's explosive birth. The story of the Big Bang begins with a discovery that rocked the scientific world in the 1960s. Astronomers Arno Penzias and Robert Wilson stumbled upon a faint, persistent hum of radiation coming from all directions in the sky. This was the cosmic microwave background radiation, the afterglow of the Big Bang itself. Imagine it as the faint echo of a colossal explosion, reverberating across the cosmos for over 13 billion years. This discovery was the smoking gun, the proof that the universe had a fiery, dynamic beginning. But the Big Bang wasn't just an explosion in the conventional sense. It was the rapid expansion of space itself, a sudden unfurling of reality from an unimaginably dense and hot state. In the first fraction of a second, the universe underwent a process called inflation, expanding faster than the speed of light. Think of it like a balloon inflating in an instant, stretching the fabric of space to cosmic proportions. This period of inflation set the stage for everything that followed, from the formation of galaxies to the emergence of life itself. In those first moments, the universe was a seething cauldron of energy. Quarks, the building blocks of protons and neutrons, danced in a primordial soup, colliding and combining as the universe cooled. Within minutes, the first atomic nuclei formed, a process known as nucleosynthesis. This was the birth of the simplest elements, hydrogen and helium, the raw materials that would later form stars, planets, and even us. Yet, as much as the Big Bang explains, it also raises profound questions. What caused it? What came before? Some cosmologists suggest that the Big Bang might not be the absolute beginning, but rather a transition from a previous state. Theories like the bouncing universe propose that our universe could be one in a series of endless cycles, expanding and contracting like the breath of a cosmic giant. Others speculate about a multiverse where our Big Bang was just one event among countless others, each giving rise to its own unique universe. The Big Bang is more than a scientific theory. It's a story of origins, a narrative that connects us to the very fabric of reality. It reminds us that the universe is dynamic, ever-changing, and full of mysteries waiting to be uncovered. And as we peer back into those first moments, we're left with a sense of awe at the sheer scale of existence and a burning curiosity about what lies beyond the boundaries of our understanding. This journey into the cosmic genesis leads us to another fascinating concept: cosmic inflation. If the Big Bang was the spark, inflation was the explosive force that shaped the universe into what we see today. But what exactly is inflation, and how did it set the stage for everything that followed? Let's explore this next chapter in the story of our universe. Cosmic inflation is one of the most revolutionary ideas in modern cosmology. a theory that explains how the universe went from a tiny, hot speck to the vast, intricate cosmos we see today, all in the blink of an eye. Imagine blowing up a balloon, but instead of inflating at a steady pace, it expands faster than the speed of light, doubling in size over and over again in fractions of a second. This is what scientists believe happened in the first moments after the Big Bang, a period of exponential growth that shaped the very structure of our universe. The concept of inflation was first proposed in the 1980s by physicist Alan Guth, who was trying to solve two puzzling mysteries, the horizon problem and the flatness problem. The horizon problem asks why the universe looks so remarkably uniform in every direction. If you look at the cosmic microwave background radiation, the oldest light in the universe, it appears almost perfectly smooth with only tiny fluctuations. But without inflation, there wouldn't have been enough time for heat and light to travel across the early universe, creating this uniformity. Inflation solves this by stretching space so rapidly that regions once close together were pulled far apart, smoothing out any irregularities. The flatness problem, on the other hand, deals with the geometry of the universe. Observations show that space is almost perfectly flat, meaning that the density of matter and energy in the cosmos is finely balanced. Without inflation, this balance would require an impossibly precise tuning of conditions in the early universe. But inflation naturally flattens space, much like how blowing up a balloon makes its surface smoother and flatter. Evidence for inflation comes from the cosmic microwave background itself. The tiny temperature fluctuations in this ancient light, often described as the fingerprints of the Big Bang, match predictions made by inflation models. These fluctuations are the seeds of all structure in the universe, the slight variations in density that eventually grew into galaxies, stars, and planets. Without inflation, these structures might never have formed. But what caused inflation? Physicists believe it was driven by a mysterious field of energy, often called the inflaton field, which permeated the early universe. As this field decayed, it released energy, fueling the rapid expansion. Think of it like a coiled spring suddenly releasing its tension, propelling the cosmos outward in an explosive burst. Once inflation ended, the energy of the inflaton field transformed into the particles and radiation that filled the young universe, setting the stage for everything that followed. While inflation answers many questions, it also raises new ones. For instance, could inflation have happened more than once? Some theories suggest that our universe might be just one bubble in a vast multiverse, with other bubbles undergoing their own inflationary periods. It's a mind-bending idea that pushes the boundaries of our understanding. As we piece together the story of cosmic inflation, we gain a deeper appreciation for the universe's complexity and elegance. It's a reminder that the cosmos is not static but dynamic, shaped by forces that are both profound and subtle. And as we look at the large-scale structure of the universe, the vast cosmic web of galaxies and clusters, we see the enduring legacy of those first moments, a testament to the power of inflation to shape reality itself. This journey into the early universe leads us to another fascinating question. How did these initial conditions give rise to the intricate structures we see today? The answer lies in the delicate interplay of gravity, dark matter, and the seeds of cosmic structure planted by inflation, a story we'll explore next. Picture the universe not as a random scattering of stars and galaxies, but as an intricate, interconnected network, a vast cosmic web stretching across billions of light years. This is the universe's skeleton, a structure so immense and delicate that it defies imagination. Made up of galaxies, gas, and dark matter, the cosmic web is the result of gravitational forces weaving together the fabric of reality over billions of years. It's a masterpiece of chaos and order, shaping everything from the tiniest galaxies to the largest superclusters in the cosmos. At the heart of this cosmic tapestry is dark matter, the invisible scaffolding that holds the web together. Without it, galaxies would drift apart and the universe would lack the structure we see today. Dark matter's gravitational pull acts like an unseen hand, guiding the formation of filaments, long, thread-like structures that connect galaxies and clusters. These filaments are the threads of the cosmic web, crisscrossing the universe in a pattern that resembles a spider's intricate silk. But how do we see something so vast and delicate? The answer lies in the power of modern telescopes and computer simulations. Observations from instruments like the Hubble Space Telescope and the Sloan Digital Sky Survey have mapped the web's structure, revealing its stunning complexity. Meanwhile, supercomputer simulations recreate the universe's evolution, showing how tiny fluctuations in the early cosmos grew into the web we see today. It's like watching a cosmic ballet unfold, with galaxies and dark matter dancing to the tune of gravity. Astronomers describe the cosmic web as the universe's backbone, a framework that shapes the birth and evolution of galaxies. Galaxies form at the intersections of filaments where gas and dark matter accumulate, creating the perfect conditions for stars to ignite. Over time, these galaxies grow, merge, and evolve, tracing the web's intricate patterns. It's a process that's still unfolding, with the web continuing to shape the universe's destiny. The cosmic web isn't just a scientific curiosity, it's a reminder of how interconnected the universe truly is. Every galaxy, every star, and even every atom in your body is part of this vast network, a testament to the forces that bind the cosmos together. And as we unravel its mysteries, we gain a deeper understanding of our place within it. But the cosmic web is more than just a static structure. It's a dynamic, ever-changing tapestry. Within its threads lie some of the universe's most extreme environments, galaxy clusters. These massive collections of galaxies, bound together by gravity, are the web's most luminous nodes, shining with the light of millions of stars. Yet they're also home to some of the most profound mysteries in the cosmos. What secrets do these clusters hold, and what can they tell us about the universe's past, present, and future? Let's explore this next chapter in the story of the cosmic web. Galaxy clusters are the universe's grandest metropolises, sprawling cities of stars, gas, and dark matter that stretch across millions of light years. These colossal structures are the largest gravitationally bound systems in existence, home to thousands of galaxies, each with billions of stars of their own. Imagine a city so vast that its suburbs are entire galaxies. Its streets are streams of superheated gas, and its skyline is defined by the glow of supermassive black holes. This is the awe-inspiring scale of a galaxy cluster, a cosmic hub where gravity reigns supreme. The formation of these stellar metropolises begins with the cosmic web. As dark matter filaments intersect, they create dense regions where gas and galaxies accumulate. Over billions of years, gravity pulls these galaxies closer together, forming clusters that can weigh as much as a quadrillion suns. It's a process that's both gradual and dramatic, shaped by the relentless tug of gravity and the intricate dance of dark matter. Within these clusters, galaxies aren't isolated islands, they're dynamic, interacting neighbors. Some collide and merge, triggering bursts of star formation and creating new galaxies. Others orbit the cluster's core, drawn by the immense gravitational pull of its central region. This core is often dominated by a giant elliptical galaxy, a behemoth that has grown by consuming its smaller neighbors. Surrounding it is a halo of dark matter, an invisible cocoon that holds the cluster together. But the galaxies are just one part of the story. Between them lies a sea of superheated gas known as intracluster gas, which can reach temperatures of millions of degrees. This gas glows in X-rays, revealing the cluster's energetic heart. It's a turbulent environment where shock waves from galaxy collisions and supermassive black hole activity ripple through the gas, shaping its structure and dynamics. Speaking of black holes, they play a starring role in galaxy clusters. At the center of many clusters lies a supermassive black hole, often billions of times more massive than our Sun. These cosmic giants aren't just destructive forces, they're also creators. As they feed on surrounding gas, they unleash powerful jets of energy that can heat the intracluster gas, preventing it from cooling and forming new stars. It's a feedback loop that regulates the cluster's evolution, balancing creation and destruction on a cosmic scale. Astrophysicists study galaxy clusters not just for their sheer size and complexity, but for what they reveal about the universe's history. Because they form in the densest regions of the cosmic web, clusters act as cosmic laboratories, offering insights into the distribution of dark matter, the behavior of gravity, and the evolution of galaxies. They're also key to understanding the universe's expansion, as their immense gravity can bend light, creating gravitational lenses that magnify distant objects behind them. Galaxy clusters are more than just collections of stars and gas. They're living, evolving systems that tell the story of the cosmos. They remind us that the universe is a place of both harmony and chaos, where gravity weaves galaxies into vast tapestries and black holes shape the destiny of entire clusters. As we marvel at these cosmic cities, we're led to another fascinating question. What about the stars themselves? How do these building blocks of galaxies form, live, and die? The life cycles of stars are as varied and dramatic as the galaxies they inhabit. A story that takes us from the birth of starlight to the explosive deaths that seed the cosmos with new elements. Let's explore this next chapter in the universe's grand narrative. Stars are the universe's ultimate alchemists, transforming the simplest elements into the building blocks of life itself. Their journeys from birth in the cold, dark depths of space to their fiery, explosive ends are some of the most dramatic stories in the cosmos. Every star begins its life in a molecular cloud, a vast, swirling nursery of gas and dust. These clouds, often hundreds of light years across, are the raw material of the universe, the cosmic cradles where stars are born. As gravity pulls these clouds together, pockets of gas begin to collapse, growing denser and hotter. At the heart of these collapsing clouds, a protostar forms, a young, glowing ember that will one day ignite into a full-fledged star. It's a slow, delicate process taking millions of years, but once nuclear fusion begins in the star's core, it marks the start of a brilliant, energy-filled life. Nuclear fusion is the engine that powers every star, a process where hydrogen atoms collide and fuse to form helium, releasing immense amounts of energy in the process. This energy radiates outward, balancing the star against the crushing force of its own gravity. For most of a star's life, this delicate equilibrium holds, allowing it to shine steadily for billions of years. But stars don't live forever. Their fates are determined by their mass. Smaller stars, like our Sun, burn through their hydrogen fuel slowly, eventually swelling into red giants before shedding their outer layers and leaving behind a dense, glowing core called a white dwarf. These stellar embers slowly cool over eons, fading into the darkness of space. For more massive stars, the story is far more explosive. As they exhaust their fuel, they begin to fuse heavier elements like carbon, oxygen, and even iron in their cores. This process, known as stellar nucleosynthesis, is the universe's way of creating the elements that make up planets, life, and even us. But when a massive star's core can no longer support fusion, it collapses under its own gravity, triggering a cataclysmic explosion called a supernova. Supernovae are among the most powerful events in the universe, outshining entire galaxies for a brief moment. In their aftermath, they leave behind either a neutron star, an ultra-dense remnant spinning at incredible speeds, or, in the case of the most massive stars, a black hole. These remnants are the cosmic fingerprints of stellar death, carrying the story of the star's explosive end into the future. The life cycles of stars are more than just cosmic drama, they're the reason we exist. Every atom of carbon in your body, every speck of iron in your blood, was forged in the heart of a dying star. This process, often called cosmic alchemy, is the universe's way of recycling matter, transforming the simplest elements into the complex chemistry that makes life possible. Astronomers marvel at the diversity of stellar fates, from the quiet fading of white dwarfs to the violent births of neutron stars and black holes. Each star's journey is unique, shaped by its mass, composition, and environment. And as we study these stellar life cycles, we gain a deeper appreciation for the interconnectedness of the cosmos. But the story doesn't end with a star's death. The remnants of these explosions, neutron stars, black holes, and clouds of gas enriched with heavy elements become the seeds of new stars, planets, and perhaps even life. This cycle of creation and destruction is the heartbeat of the universe, a rhythm that has shaped the cosmos since its earliest days. As we explore the remnants of stellar explosions, we'll uncover even more mysteries, from the bizarre physics of neutron stars to the enigmatic nature of black holes. These remnants are not just the end of a star's story, they're the beginning of new chapters in the universe's grand narrative. Let's zoom in on one of the most extreme and fascinating objects in the cosmos, neutron stars. Born from the fiery aftermath of a supernova, these stellar remnants are unlike anything else in the universe. Imagine taking the mass of the Sun, a sphere nearly 1.4 million kilometers across, and crushing it into a city-sized ball just 20 kilometers wide. That's the mind-bending density of a neutron star, where a single teaspoon of material would weigh billions of tons. These cosmic powerhouses are not just dense, they're laboratories for some of the most extreme physics imaginable. When a massive star exhausts its fuel and collapses, its core is compressed into a neutron star. The intense pressure forces protons and electrons to merge, creating a sea of neutrons. The result is an object so dense that it defies our everyday understanding of matter. The surface of a neutron star is a solid crust, but beneath it lies a superfluid core, a state of matter so strange it behaves like a frictionless liquid. And then there's the gravity, so strong that it bends light into a visible halo around the star, a phenomenon called gravitational lensing. But neutron stars aren't just exotic curiosities, they're also cosmic timekeepers. Some neutron stars spin at incredible speeds, rotating hundreds of times per second. These rapidly spinning neutron stars are called pulsars, and they emit beams of radiation from their magnetic poles. As the pulsar spins, these beams sweep across space like the light from a lighthouse, creating a rhythmic pulse that can be detected from Earth. This regular ticking has made pulsars invaluable tools for astronomers, serving as natural cosmic clocks and even helping test Einstein's theory of general relativity. The magnetic fields of neutron stars are another realm of extremes. Magnetars, a special class of neutron stars, have fields trillions of times stronger than Earth. These fields are so powerful that they can distort the shape of atoms and create starquakes, violent tremors on the neutron star's surface that release bursts of energy. In fact, some of the most energetic explosions in the universe, known as gamma-ray bursts, are thought to originate from these magnetic behemoths. Astrophysicists are drawn to neutron stars not just for their extremes, but for what they reveal about the fundamental laws of physics. By studying their behavior, scientists can probe the nature of matter under conditions that can't be replicated on Earth. Neutron stars also offer clues about the universe's most mysterious forces, from gravity to the strong nuclear force that binds atomic nuclei together. Perhaps the most remarkable thing about neutron stars is their role in the cosmic cycle of life and death. When they form, they seed the surrounding space with heavy elements forged in their cores, enriching the universe with the building blocks of planets and life. And when neutron stars collide, they create ripples in space-time known as gravitational waves, events that have been detected by observatories like LIGO. These collisions are cosmic alchemists producing gold, platinum, and other precious elements in their aftermath. Neutron stars are more than just remnants of stellar explosions. They're windows into the extremes of the universe, places where the laws of physics are pushed to their limits. But if you think neutron stars are extreme, prepare to be amazed by their even more mysterious cousins, black holes. These cosmic enigmas take the concept of density and gravity to an entirely new level, bending not just light but the very fabric of space and time. At the heart of nearly every galaxy lies a cosmic monster, a supermassive black hole so immense it defies comprehension. These galactic behemoths, weighing millions to billions of times the mass of our Sun, are not just gravitational traps, they are engines of creation and destruction, shaping the very fabric of the galaxies they inhabit. From their mysterious origins to their explosive influence on the cosmos, supermassive black holes are among the most fascinating and enigmatic objects in the universe. Supermassive black holes are thought to form in two primary ways. Some may have grown from the seeds of smaller black holes, remnants of the first massive stars that formed in the early universe. Over billions of years, these seeds grew by devouring gas, dust, and even other stars, their gravity pulling in more and more matter until they reached staggering sizes. Others might have formed directly from the collapse of massive clouds of gas, bypassing the star stage entirely and becoming black holes almost instantly. Regardless of their origins, these giants have one thing in common: an insatiable hunger for matter. As matter spirals toward a supermassive black hole, it doesn't just disappear quietly. Instead, it forms a swirling disk of superheated gas and dust, glowing so brightly that it can outshine entire galaxies. This accretion disk is a maelstrom of energy, where friction and magnetic fields heat the material to millions of degrees, releasing torrents of radiation. But the black hole's influence doesn't stop there. Some of the material is funneled into powerful jets, streams of particles that shoot out at nearly the speed of light, stretching thousands of light years into space. These jets are cosmic lighthouses, illuminating the surrounding universe and carving out vast bubbles in the intergalactic medium. The impact of supermassive black holes on their host galaxies is profound. They regulate star formation, heating up gas and preventing it from cooling into new stars. In some cases, they can even trigger waves of star birth, their jets compressing gas clouds and igniting stellar nurseries. This delicate balance between creation and destruction makes supermassive black holes key players in the evolution of galaxies. Without them, the universe as we know it might look very different. Astronomers have long been captivated by these cosmic giants, studying them with everything from radio telescopes to space-based observatories. One of the most famous examples is Sagittarius, a star, the supermassive black hole at the center of our Milky Way. Though it's relatively quiet today, its past may have been filled with violent outbursts shaping the galaxy we call home. Further afield, quasars, active galaxies powered by supermassive black holes, shine with the light of 1 trillion suns, offering glimpses into the early universe. But as much as we've learned about supermassive black holes, they remain shrouded in mystery. How do they grow so massive? What happens to matter that crosses the event horizon? And what role do they play in the larger cosmic web? These are questions that push the boundaries of our understanding, inviting us to explore the extremes of space and time. As we contemplate the immense power of supermassive black holes, we're also led to a deeper question: what happens when the laws of physics break down? To answer that, we must venture into the strange and counterintuitive world of quantum mechanics, where the rules of the everyday universe no longer apply. This next step in our journey promises to challenge our understanding of reality itself. Now, let's step into a realm where the rules of the everyday world no longer apply. A place where particles can exist in two places at once, where objects are connected across vast distances instantaneously, and where reality itself seems to bend to the whims of probability. This is the strange and counterintuitive world of quantum mechanics, a framework that governs the behavior of the smallest particles in the universe. While it might sound like science fiction, quantum mechanics is one of the most well-tested and successful theories in science, yet it challenges everything we think we know about reality. At the heart of quantum mechanics is the concept of superposition, the idea that particles can exist in multiple states simultaneously until they are observed or measured. Imagine a coin spinning in the air. It's neither heads nor tails while it's spinning, but both at the same time. Only when it lands does it choose a state. In the quantum world, particles like electrons can be in multiple states at once, a phenomenon that defies our everyday intuition but has been confirmed by countless experiments. This leads us to another mind-bending concept: wave-particle duality. Quantum particles, such as photons of light, can behave like both particles and waves depending on how they're observed. In the famous double-slit experiment, particles shot through two slits create an interference pattern on a screen, as if they were waves, but when observed, they behave like discrete particles. It's as if the very act of looking changes their behavior, a notion that has puzzled scientists for decades. Then there's quantum entanglement, a phenomenon Albert Einstein famously called spooky action at a distance. When two particles become entangled, their properties are linked no matter how far apart they are. Measure one, and the other instantly takes on a corresponding state, even if it's light years away. This instantaneous connection seems to defy the speed of light, raising questions about the nature of space and time. Could the universe be more interconnected than we thought? These strange behaviors have profound implications for our understanding of reality. For one, they suggest that the universe might be fundamentally probabilistic rather than deterministic. At the quantum level, events aren't set in stone. They're governed by probabilities with outcomes that can't be predicted with absolute certainty. This randomness lies at the core of quantum mechanics, challenging the classical view of a clockwork universe where everything follows fixed laws. But quantum mechanics isn't just about tiny particles. It has big implications for the cosmos as a whole. One of the greatest challenges in modern physics is reconciling quantum mechanics with Einstein's theory of general relativity, which describes gravity and the large-scale structure of the universe. While quantum mechanics excels at explaining the behavior of particles, general relativity governs the motion of planets, stars, and galaxies. Combining these two frameworks into a single theory of everything remains one of the most elusive goals in science. Physicists have proposed various approaches to this problem, from string theory to loop quantum gravity, but the mystery persists. Some suggest that the key lies in the quantum vacuum, the seemingly empty space that's actually teeming with energy and virtual particles popping in and out of existence. This vacuum might hold clues to the nature of dark energy, the expansion of the universe, and even the birth of reality itself. So, what does all this mean for our understanding of the universe? Is reality fundamentally random, or are there deeper laws we've yet to uncover? These questions don't just challenge science, they challenge our very perception of existence. As we explore the quantum realm, we're not just uncovering the rules of the smallest scales, we're redefining what it means to live in a universe that's far stranger and more interconnected than we ever imagined. And as we peer into the quantum vacuum, we're met with yet another mystery. What lies beneath the surface of nothingness? This question takes us into the heart of one of the most profound enigmas in physics, a mystery that might hold the key to understanding the fabric of reality itself. What if the vacuum of space, seemingly empty and silent, is actually alive with energy, a hidden sea of activity that defies our most basic assumptions about reality? This is the quantum vacuum, the lowest energy state of space, and it's far from the lifeless void we imagine. While it appears empty to the naked eye, the quantum vacuum is a dynamic, seething realm where particles pop in and out of existence in a constant dance of creation and annihilation. It's a bubbling cosmic soup, a place where the rules of classical physics no longer apply, and the fabric of reality itself becomes fluid. At the heart of this phenomenon is the concept of virtual particles. According to quantum mechanics, empty space isn't truly empty. It's filled with fluctuations in energy that give rise to pairs of particles and antiparticles. These pairs appear for the briefest of moments before annihilating each other, leaving no trace behind. It's as if the vacuum is alive, constantly simmering with potential, a stage where the universe rehearses its smallest acts of creation. One of the most striking demonstrations of the quantum vacuum's activity is the Casimir effect. When two uncharged metal plates are placed extremely close together in a vacuum, they're pushed together by an invisible force. This happens because the space between the plates restricts the types of virtual particles that can form, creating a pressure imbalance. It's a tangible effect of the quantum vacuum, a reminder that what we perceive as empty is anything but. The quantum vacuum also plays a starring role in one of the most famous predictions of modern physics, Hawking radiation. Near the event horizon of a black hole, the intense gravitational field can pull apart virtual particle pairs. One particle falls into the black hole while the other escapes as radiation. Over time, this process causes black holes to lose mass and energy, slowly evaporating. It's a stunning example of how the quantum vacuum interacts with the most extreme environments in the universe, blurring the line between nothingness and somethingness. But what does this mean for us? Could the quantum vacuum be more than just a cosmic curiosity? Some physicists have speculated that it might hold the key to unlocking new sources of energy. Imagine tapping into the boundless energy of the vacuum itself, harnessing the fluctuations that power the universe. While this idea remains speculative, it's a testament to the profound potential hidden within the quantum realm. The quantum vacuum challenges our understanding of reality, suggesting that the universe is far more interconnected and dynamic than we ever imagined. It's a reminder that what we perceive as empty is teeming with life, a hidden layer of existence that shapes the cosmos in ways we're only beginning to understand. And as we explore this strange and mysterious realm, we're led to an even more radical idea. Could the universe itself be a hologram, a projection of information encoded on its boundaries? This is the tantalizing concept of the holographic universe, a theory that blurs the line between reality and illusion, a mystery we'll explore next. What if the universe we perceive with its vast galaxies, shimmering stars, and endless expanse isn't truly three-dimensional? What if it's all a projection, a cosmic illusion encoded on a two-dimensional surface? This is the radical idea at the heart of the holographic principle, a theory that challenges our most fundamental assumptions about space, time, and reality itself. It's a concept born from the enigmatic behavior of black holes and the intricate mathematics of string theory, and it might just hold the key to unlocking one of the greatest mysteries in physics, the unification of quantum mechanics and gravity. The story of the holographic principle begins with black holes, those cosmic enigmas where gravity becomes so intense that not even light can escape. In the 1970s, physicist Jacob Bekenstein made a startling discovery. The entropy or disorder of a black hole is proportional to the area of its event horizon, not its volume. This was a profound insight, suggesting that all the information about what falls into a black hole could be encoded on its two-dimensional surface. Later, Stephen Hawking showed that black holes emit radiation, slowly losing mass and energy over time, but this raised a troubling question. What happens to the information about the matter that fell in? The holographic principle emerged as a solution, proposing that the information isn't lost. It's stored on the black hole's surface like a cosmic hard drive. This idea didn't stay confined to black holes. In the 1990s, physicist Gerard T. Hooft and string theorist Leonard Susskind expanded it, suggesting that the entire universe might work the same way. Just as a hologram encodes a three-dimensional image on a flat surface, the holographic principle posits that the universe's information could be encoded on a two-dimensional boundary. It's as if our three-dimensional world is a projection, a kind of cosmic movie played out on a flat screen. But how could this be possible? String theory, one of the most ambitious frameworks in physics, offers a clue. In string theory, the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings exist in higher dimensional spaces, and their interactions could create the illusion of a three-dimensional world. The holographic principle takes this a step further, suggesting that the string's information could be encoded on a lower dimensional surface, much like a hologram. The implications of this idea are staggering. If the universe is a hologram, it would mean that space and time aren't fundamental but emergent properties, arising from the interactions of information on a two-dimensional surface. This could provide a way to unify quantum mechanics, which governs the very small, with general relativity, which describes the very large. It's a potential bridge between two theories that have long seemed incompatible, offering a new perspective on the nature of reality. So, is our three-dimensional world just an illusion? Could the universe be a projection, a cosmic hologram? These questions don't just challenge our understanding of physics, they force us to rethink what it means to exist. The holographic principle invites us to consider that reality might be far stranger than we ever imagined, a shimmering mirage woven from the threads of information. But this raises another profound question. If the universe is a projection, what about consciousness? Could our perception of reality be part of the hologram, shaped by the same principles that govern the cosmos? This connection between the nature of the universe and the nature of our minds is a mystery that takes us to the very edge of science and philosophy, a journey we'll explore as we dive deeper into the hidden realms of the cosmos. What if the universe isn't just a place we inhabit, but something we're deeply woven into, something that might even depend on us to exist? This is the startling idea at the heart of the connection between consciousness and the cosmos. For centuries, philosophers and scientists have debated the nature of consciousness, that mysterious quality that allows us to experience the world. But what if consciousness isn't just a byproduct of the brain? What if it's a fundamental feature of the universe itself, as essential as space, time, and matter? One of the most intriguing theories along these lines is panpsychism, the idea that consciousness is a universal property, present even in the smallest particles. Think of it like this: just as electrons have charge and mass, they might also possess a rudimentary form of awareness. This doesn't mean electrons think or feel in the way we do, but rather that consciousness could be a basic building block of reality, like an ingredient in the cosmic recipe. It's a radical idea, but one that's gaining traction among some philosophers and physicists who see it as a way to bridge the gap between mind and matter. Then there's the observer effect in quantum mechanics, a phenomenon that hints at a deep connection between consciousness and the fabric of reality. In experiments like the famous double-slit test, particles behave differently when they're observed. It's as if the act of observation itself influences the outcome, collapsing the particle's wave function from a state of probability into a definite reality. Some interpretations suggest that consciousness plays a role in this process, that the universe requires an observer to choose a state. Of course, this interpretation is hotly debated, but it raises a profound question. Is the universe not just something we observe, but something that responds to us? Philosophers have long grappled with these ideas, from ancient thinkers like Plato, who saw the mind as a reflection of a greater cosmic order, to modern figures like David Chalmers, who coined the term the hard problem of consciousness. The relationship between mind and matter has been a central mystery. Chalmers argues that even if we fully understand how the brain works, we still won't explain why we have subjective experiences, why it feels like something to be alive. This gap between the physical and the experiential is what makes consciousness so puzzling and so fascinating. Scientists, too, have begun to explore these ideas. Some, like physicist Sir Roger Penrose, suggest that consciousness might be rooted in the strange quantum processes happening in our brains. Others propose that the universe itself might be conscious, a vast, self-aware system in which we are just tiny threads. Imagine the universe as a kind of mirror, reflecting itself through the minds of conscious beings. In this view, we're not just observers of the cosmos, we're participants, integral to its unfolding story. This perspective doesn't just challenge our understanding of the universe, it redefines our place within it. If consciousness is fundamental, then the search for meaning becomes a cosmic endeavor, a quest to understand not just the stars and galaxies, but the very nature of awareness itself. And if the universe is, in some sense, aware, what does that mean for other forms of consciousness that might exist out there? This leads us to one of the most profound questions in science: are we alone? The search for extraterrestrial intelligence, or SETI, is more than just a hunt for alien life. It's a quest to understand whether consciousness is a rare spark or a universal flame. If we were to discover another intelligent species, it wouldn't just change our view of the cosmos. It might reveal something profound about the nature of consciousness itself. As we ponder these questions, we're reminded that the universe is not just a place of matter and energy, but of mystery and possibility. Whether consciousness is a cosmic accident or a fundamental feature, it invites us to see the universe not as something separate from us, but as something we're deeply connected to, a vast, unfolding story in which we play a vital part. The search for alien life is one of humanity's most profound quests, a journey that asks not just whether we're alone in the universe, but what it means to share the cosmos with others. For decades, scientists have been scanning the skies, hunting for signs of intelligent life beyond Earth through initiatives like the Search for Extraterrestrial Intelligence, or SETI. Using powerful instruments like radio telescopes, SETI listens for signals that might betray the presence of distant civilizations. These efforts aren't just about finding aliens, they're about understanding our place in the universe and the nature of life itself. One of the primary tools in this search is the radio telescope, designed to detect electromagnetic signals from space. Radio waves are ideal for interstellar communication because they can travel vast distances without being absorbed by cosmic dust. SETI researchers focus on narrowband signals, those with a specific frequency, because natural cosmic phenomena like pulsars or quasars tend to produce broadband signals. A narrowband signal, on the other hand, could indicate intentional communication, a technosignature from an advanced civilization, but the search doesn't stop at radio waves. Scientists are also looking for other technosignatures, such as laser pulses, megastructures like Dyson spheres, or even atmospheric pollution on distant exoplanets. These are signs that a civilization has harnessed energy on a massive scale, leaving detectable imprints on their environment. It's a bit like searching for a needle in a cosmic haystack, but the stakes and the potential rewards are unimaginably high. Yet, despite decades of searching, we've found nothing. This silence raises a haunting question. Where is everyone? Known as the Fermi paradox, this puzzle asks why, in a universe so vast and ancient, we haven't encountered any evidence of extraterrestrial life. One possible answer is that intelligent civilizations are incredibly rare, or that they self-destruct before they can develop interstellar communication. Others suggest that advanced civilizations might be so different from us that their signals are unrecognizable, or that they've chosen to remain hidden. Astronomers have proposed countless theories to explain the paradox, from the idea that Earth is uniquely suited for life to the possibility that alien civilizations are too far away for us to detect. Some even speculate that we might be living in a kind of cosmic zoo, where advanced beings observe us without interference. Whatever the answer, the Fermi paradox reminds us of how little we truly know about the universe and the possibilities it holds. The search for alien life isn't just about finding others, it's about understanding ourselves. If we were to discover even a single signal from another civilization, it would fundamentally change how we see our place in the cosmos. Are we alone, or is the universe teeming with life? The question lingers, unanswered but endlessly compelling. As we ponder the possibilities of intelligent life, we're also led to another fascinating question. What about life in its simplest forms? If we broaden our search to include microbial life, the odds of finding something increase dramatically. And when we look to extreme environments on Earth, places like deep-sea hydrothermal vents, acidic hot springs, or frozen Antarctic lakes, we find organisms thriving in conditions once thought impossible. These extremophiles, as they're called, suggest that life might be far more adaptable and widespread than we ever imagined. Could similar life exist on distant moons like Europa or Enceladus, or in the methane lakes of Titan? The search for alien life isn't just about finding intelligence, it's about discovering the resilience and diversity of life itself. Hidden deep beneath Earth's oceans, buried in scorching hot springs, or clinging to life in the frozen deserts of Antarctica, there exists a group of organisms that defy our understanding of where life can thrive. These are extremophiles, tiny, resilient beings that survive in conditions once thought to be completely inhospitable. From boiling geothermal vents to acidic lakes, they push the boundaries of what we consider habitable, offering a tantalizing glimpse into the potential for life beyond our planet. If life can flourish in such extreme environments here on Earth, could it also exist in the alien landscapes of our solar system, or even beyond? One of the most fascinating examples of extremophiles are those found near hydrothermal vents on the ocean floor. These vents, often called black smokers, spew superheated water rich in minerals into the icy darkness, creating an otherworldly environment. Yet, despite the crushing pressure, lack of sunlight, and scorching temperatures, entire ecosystems thrive here, sustained not by photosynthesis but by chemosynthesis, a process where bacteria convert chemicals like hydrogen sulfide into energy. These ecosystems are a testament to life's ingenuity, proving that even in the harshest conditions, biology finds a way. This discovery has profound implications for our search for extraterrestrial life. If life can exist in such extreme environments on Earth, why not elsewhere? Take Europa, one of Jupiter's moons, for example. Beneath its icy surface lies a vast subsurface ocean, warmed by the moon's gravitational interactions with Jupiter. Scientists believe this ocean could be twice the volume of all Earth's oceans combined, and it might host the right conditions for life: liquid water, energy sources, and potentially even organic compounds. Europa's icy shell, crisscrossed with cracks and ridges, could act as a protective barrier, shielding any potential life from the harsh radiation of space. Then there's Mars, our planetary neighbor, once home to rivers, lakes, and perhaps even an ancient ocean. While its surface is now a barren, radiation-scorched desert, evidence of past water suggests that life might have once existed there and could still exist underground. Recent missions have detected methane plumes in Mars' atmosphere, a gas that could be produced by microbial life. Astrobiologists are particularly excited about the possibility of finding extremophiles in Martian subsurface caves or beneath the polar ice caps, where conditions might be more stable and shielded from radiation. But the search doesn't stop there. Saturn's moon Enceladus, with its geysers of water vapor erupting from a subsurface ocean, and Titan, with its methane lakes and complex organic chemistry, are also prime candidates for hosting life. These moons are like alien oases in the cosmos, offering environments where extremophiles or something even more exotic might thrive. Astrobiologists often emphasize that life, as we know it, requires three key ingredients: liquid water, a source of energy, and organic molecules. But as extremophiles have shown us, life can adapt to conditions we once thought impossible. This flexibility opens up a universe of possibilities, suggesting that life might exist in forms and places we've yet to imagine. As we explore these alien habitats, we're also led to a fascinating idea. Could life have traveled between planets carried by meteorites or comets? This concept, known as Panspermia, suggests that life isn't confined to a single world but could spread across the cosmos, seeding planets and moons with the building blocks of biology. If true, it would mean that life on Earth, and perhaps elsewhere, might share a common origin, a cosmic connection that spans the stars. The study of extremophiles and alien habitats is more than just a scientific endeavor. It's a journey of imagination and discovery. It challenges us to think beyond the familiar, to consider that life might be far more resilient and widespread than we ever imagined. And as we peer into the icy oceans of Europa or the ancient riverbeds of Mars, we're reminded that the universe is full of surprises waiting to be uncovered. What if life on Earth didn't actually begin here? What if instead it arrived from the stars, carried across the cosmos on comets, asteroids, or even cosmic dust? This is the intriguing idea behind Panspermia, the theory that life might not be confined to a single planet but could spread throughout the universe, hitching rides on celestial travelers. Think of it as nature's ultimate delivery system, where life itself becomes a cosmic traveler, seeding planets and moons with the building blocks of biology. At its heart, Panspermia proposes that microorganisms, tiny, resilient life forms, could survive the harsh conditions of space, protected within the icy cores of comets or the rocky interiors of asteroids. These cosmic seeds might then be deposited on new worlds where the right conditions could allow them to thrive. It's a theory that blurs the line between Earth and the stars, suggesting that life could be a universal phenomenon, carried from one corner of the cosmos to another. But how plausible is this idea? Surprisingly, there's evidence to support it. Scientists have discovered microorganisms that can survive extreme conditions, from the vacuum of space to the intense radiation of cosmic rays. Some bacteria, like Deinococcus radiodurans, are so resilient they've earned the nickname Conan the Bacterium. These extremophiles suggest that life, once it begins, might be far tougher than we think, capable of enduring interstellar journeys. Then there's the discovery of organic molecules, the building blocks of life, on comets and asteroids. Missions like NASA's Stardust and ESA's Rosetta have found amino acids and other complex compounds in the icy debris of comets, hinting that these celestial bodies could carry the ingredients for life. Imagine a comet billions of years ago crashing into a young Earth, delivering not just water but the very molecules needed for life to emerge. Panspermia also raises fascinating questions about the origins of life. If life can travel between planets, does that mean it's more common than we think? Could life on Earth have come from Mars or even from a distant star system? Some scientists speculate that early Mars, with its once flowing rivers and lakes, might have been a more hospitable cradle for life than Earth. If so, fragments of Martian rock blasted into space by ancient impacts could have carried microbial life to our planet. The implications of panspermia are profound. If life can spread across the cosmos, it means we might not be alone, and that life elsewhere could share a common origin with life on Earth. It also suggests that the search for extraterrestrial life shouldn't be limited to planets. We might find life's fingerprints in the icy depths of comets or the dusty tails of asteroids. As we ponder the possibility of life's cosmic journey, we're also led to a larger question. What does this mean for the future of space exploration? If life can travel between worlds, could we one day become the cosmic travelers carrying Earth's biology to new planets? This idea, known as directed panspermia, raises both exciting possibilities and ethical dilemmas. Should we deliberately seed other worlds with life, or is that a step too far? The concept of panspermia invites us to see the universe not as a collection of isolated worlds, but as a connected network where life flows freely between stars and planets. It's a vision of a cosmos alive with possibility, where the story of life is written not just on Earth, but across the vast expanse of space. As we look to the future of space exploration, we're reminded that the search for life is also a search for connection, a journey to understand not just where we came from, but where we might go. And if life truly can travel the stars, then the universe might be far more vibrant, more interconnected, and more full of wonder than we ever imagined. This leads us to the next chapter in our cosmic journey, the future of space exploration. How will our quest to understand the universe shape the technologies we develop, the worlds we explore, and the life we discover? The answers lie not just in the stars, but in the choices we make as a species as we reach out to touch the infinite. As we stand on the precipice of a new era, the future of space exploration stretches before us like an uncharted ocean, vast and full of possibility. From the dusty plains of Mars to the icy moons of the outer solar system, and even the distant stars beyond, humanity's next frontier is one of bold ambition and groundbreaking innovation. But what will this future look like? What technologies will carry us to these distant worlds? And what challenges will we face along the way? One of the most exciting near-term goals is the human exploration of Mars. Space agencies like NASA and ESA, alongside private companies like SpaceX, are racing to make this dream a reality. Mars, with its ancient riverbeds and potential for subsurface water, has long captivated our imaginations. But getting there is no small feat. The journey alone takes months, and the challenges of surviving on a planet with a thin atmosphere, frigid temperatures, and intense radiation are immense. Technologies like advanced life support systems, 3D printed habitats, and even terraforming concepts are being developed to make Mars a second home for humanity. But Mars is just the beginning. Beyond the red planet lies the outer solar system, with moons like Europa, Enceladus, and Titan offering tantalizing opportunities for exploration. These icy worlds, with their subsurface oceans and complex chemistry, could hold the key to answering one of humanity's most profound questions: are we alone in the universe? Missions like NASA Europa Clipper and ESA's JUICE aim to study these moons in detail, searching for signs of life and unlocking their secrets. To reach these distant destinations, we'll need more than just traditional chemical rockets. Enter ion drives, a technology that has already revolutionized space exploration. Unlike conventional engines, ion drives use electric fields to accelerate charged particles, providing a steady, efficient thrust over long periods. This makes them ideal for deep space missions where fuel efficiency is critical. NASA's Dawn mission, which explored the asteroids Vesta and Ceres, showcased the potential of ion propulsion, and future missions could take us even farther. But what about the stars? Interstellar travel, once the stuff of science fiction, is now a topic of serious scientific discussion. Concepts like warp drives, which would bend space-time to allow faster-than-light travel, are being explored by researchers. While the energy requirements are currently beyond our reach, the theoretical groundwork laid by physicists like Miguel Alcubierre offers a tantalizing glimpse of what might one day be possible. Private companies are also playing a pivotal role in shaping the future of space exploration. SpaceX's Starship, designed to carry humans to Mars and beyond, promises to make space travel more accessible. Blue Origin and others are focusing on space tourism and infrastructure, aiming to create a sustainable presence in low Earth orbit. These efforts are not just about exploration, they're about opening the cosmos to everyone, transforming space from a distant frontier into a place where humanity can live, work, and thrive. Yet, as we reach for the stars, we must also grapple with profound ethical questions. What does it mean to colonize another planet? How do we ensure that space exploration benefits all of humanity, not just a privileged few? And what responsibilities do we have to preserve the environments of other worlds, even as we seek to make them habitable? These are questions that demand careful thought and international collaboration as we navigate the challenges and opportunities of becoming a multiplanetary species. The future of space exploration is not just about technology or discovery, it's about who we are as a species and what we aspire to become. Will we rise to the challenge, expanding our horizons and embracing the infinite possibilities of the cosmos? Or will we falter, constrained by the limits of our imagination and our willingness to take risks? As we look to the stars, we're reminded that the journey is as important as the destination. Each step we take, whether it's landing on Mars, exploring the icy moons of Jupiter, or dreaming of interstellar travel, brings us closer to understanding our place in the universe. And in that journey, we discover not just new worlds, but new possibilities for ourselves. This leads us to the next chapter in our cosmic story, the ethical implications of space colonization. How do we balance the drive to explore with the need to protect and preserve? What responsibilities do we carry as we venture into the unknown? These questions will shape not just the future of space exploration, but the future of humanity itself. As humanity sets its sights on the stars, we're faced with questions that go beyond the technical challenges of space travel. What responsibilities do we carry as we venture into the cosmos? How do we balance our drive to explore with the need to protect and preserve the environments we encounter? These ethical dilemmas are at the heart of our cosmic journey, shaping not just how we explore, but who we become as a species. One of the most pressing issues is resource exploitation. Space is often seen as a treasure trove of untapped resources, metals like platinum and gold, rare earth elements, and even water ice that could fuel future missions. Mining asteroids or the moon could provide the materials needed to build habitats, spacecraft, and even sustain life off Earth. But this raises a critical question: who owns these resources? Is space a commons for all humanity, or will it become a new frontier for exploitation, where only the wealthiest nations or corporations benefit? The Outer Space Treaty of 1967 declares that space is the province of all mankind. But as private companies like SpaceX and Blue Origin take the lead in space exploration, the line between shared heritage and private enterprise is becoming increasingly blurred. Then there's the issue of planetary protection. As we explore worlds like Mars or Europa, we risk contaminating them with Earth-based microbes, potentially jeopardizing any native life that might exist. At the same time, bringing samples back to Earth could pose a risk to our own biosphere. It's a delicate balancing act. How do we satisfy our curiosity and scientific ambitions while minimizing harm to the environments we study? Ethicists and scientists alike argue for a principle of cosmic stewardship, where we treat other worlds with the same care and respect we'd want for our own. But what if we discover extraterrestrial life? The discovery of even microbial life would be one of the most profound moments in human history, forcing us to confront questions about the rights of other beings. Do they have inherent value? Should we avoid interfering with their ecosystems, even if it means halting our own exploration? These questions challenge us to rethink our place in the universe, not as conquerors, but as humble participants in a much larger story. Philosophers have long grappled with the moral implications of space exploration. Some argue that our survival as a species depends on expanding beyond Earth, making colonization a moral imperative. Others caution against the dangers of repeating the mistakes of colonialism, where exploration often came at the expense of indigenous peoples and environments. The key, many ethicists suggest, lies in finding a middle path, one that embraces progress while upholding principles of justice, sustainability, and respect for all life, whether terrestrial or extraterrestrial. This brings us to the philosophical heart of the matter. What does it mean to be a spacefaring civilization? Are we destined to spread life and consciousness throughout the cosmos, becoming stewards of a living universe? Or will we bring our flaws and conflicts with us, repeating the same patterns of exploitation and division? These questions aren't just hypothetical, they're shaping the decisions we make today, from how we design missions to how we govern space activities. As we navigate these ethical challenges, we're reminded that space exploration is more than a technological endeavor, it's a moral one. It's an opportunity to redefine our relationship with the cosmos, to see ourselves not as separate from the universe, but as an integral part of it. And in that redefinition, we might just discover what it means to be truly human. This journey into the ethics of space exploration leads us to an even deeper question. What is the ultimate purpose of our cosmic journey? Are we seeking to conquer the stars or to understand our place within them? The answer lies not just in the stars, but in the choices we make as we reach for them. As we peer into the vastness of the cosmos, we're not just uncovering the secrets of stars, galaxies, and black holes. We're also confronting questions that have haunted humanity for millennia. What is our place in the universe? What does it mean to exist in a cosmos so immense and ancient that it defies comprehension? These are the questions at the heart of cosmic philosophy, a field that bridges the gap between science and the deepest mysteries of the human experience. For centuries, philosophers have wrestled with the implications of our place in the universe. Ancient thinkers like Aristotle and Plato saw the cosmos as an ordered, harmonious system, with humanity at its center. But as our understanding of the universe has grown, that perspective has shifted dramatically. We now know that Earth is just one planet orbiting an average star, in one of billions of galaxies scattered across a universe that's nearly 14 billion years old. This humbling realization forces us to ask, if we're so small, does our existence have any meaning at all? This question has sparked some of the most profound reflections in both philosophy and science. The 20th century philosopher Carl Sagan famously said, "We are a way for the cosmos to know itself." In this view, humanity isn't just an accident of evolution, we're the universe becoming conscious, a way for the cosmos to reflect on its own existence. It's a perspective that transforms our sense of purpose, suggesting that our quest for understanding is part of something much larger than ourselves. But what does it mean to be conscious in a universe that's mostly dark and silent? The vast majority of the cosmos is empty space, filled with the invisible forces of dark matter and dark energy. Against this backdrop, life, and particularly intelligent life, seems almost miraculous. Some scientists, like the astrobiologist Caleb Scharf, argue that life might be a rare and precious phenomenon, a flicker of light in an otherwise cold and indifferent universe. Others, inspired by the multiverse theory, suggest that life could be more common than we think, existing in countless other realities across an infinite expanse. These ideas raise another profound question. What is our responsibility as conscious beings in the cosmos? If we're the universe's way of understanding itself, does that mean we have a duty to explore, to learn, and to protect the fragile spark of life we carry? Philosophers like Thomas Berry have argued that humanity must adopt a cosmic perspective, recognizing our interconnectedness with the universe and acting as stewards of the Earth and potentially other worlds. At the same time, cosmology has also reshaped our understanding of time and existence. The universe isn't static, it's dynamic, expanding, and evolving. In this context, life isn't a fixed point but a process, a fleeting moment in the grand sweep of cosmic history. This realization challenges us to find meaning not in permanence, but in the beauty and wonder of the present moment. One of the most intriguing ideas to emerge from this line of thought is the concept of cosmic consciousness, the idea that the universe itself might possess a form of awareness. While this idea is still speculative, it invites us to consider that consciousness might not be limited to biological organisms. Could the universe in some way be conscious of itself? And if so, what role do we play in that awareness? These questions don't just challenge our understanding of the cosmos, they challenge our understanding of ourselves. They invite us to see humanity not as separate from the universe, but as an integral part of it, woven into the fabric of reality in ways we're only beginning to comprehend. As we reflect on our place in the cosmos, we're reminded that the universe is more than just a collection of stars and galaxies. It's a story, a vast and unfolding narrative in which we are both participants and storytellers. And as we continue to explore, to question, and to wonder, we're not just seeking answers, we're adding our own chapter to that story, one that will echo through the ages long after we're gone. This journey into cosmic philosophy leads us to an even deeper mystery, the nature of consciousness itself. What is it, and how does it arise? These questions take us to the very edge of science and philosophy, where the boundaries of the known and the unknown blur in fascinating ways. What if the universe itself is awake, not just a collection of stars and galaxies, but a vast, interconnected mind, aware of its own existence? This is the provocative idea behind cosmic consciousness, a state of awareness that transcends individual minds and connects with the very fabric of reality. It's a concept that has fascinated mystics, philosophers, and scientists alike, offering a vision of the cosmos not as a lifeless machine, but as a living, thinking entity. Philosophers have long pondered the idea of a universal mind. Ancient traditions, from Eastern philosophies to indigenous cosmologies, often describe the universe as a single, interconnected whole, where every part reflects the greater whole. In Hinduism, for example, the concept of Brahman represents the ultimate reality, a cosmic consciousness that permeates everything. Similarly, mystics across cultures have spoken of moments of transcendence, where the boundaries between self and universe dissolve, and they experience a profound connection to something greater. In the modern era, scientists have begun to explore these ideas through the lens of physics and neuroscience. Some, like physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, propose that consciousness might arise from quantum processes in the brain, suggesting a deep connection between the mind and the fundamental nature of reality. Others, like physicist David Bohm, have argued that the universe operates as a unified whole, with consciousness emerging as an intrinsic property of this interconnected system. Imagine the universe not as a collection of separate objects, but as a vast network where every particle, every star, and every galaxy is part of a single dynamic web. In this view, consciousness isn't confined to individual organisms, it's a fundamental feature of the cosmos itself. The universe, in a sense, becomes aware of itself through the experiences of conscious beings like us. It's as if the cosmos is awakening to its own existence, one mind at a time. This idea raises profound questions about the nature of reality. If the universe is conscious, does that mean it has intentions or desires? Could it be guiding its own evolution, shaping the course of stars and galaxies in ways we don't yet understand? While these questions might sound speculative, they invite us to rethink our place in the cosmos, not as passive observers, but as active participants in a living, evolving universe. One intriguing connection to this idea lies in the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light, which fills the entire universe, is like a snapshot of the cosmos in its infancy. Some scientists have suggested that the patterns in this background radiation could hold clues to the universe's deeper structure, perhaps even its consciousness. While this remains a speculative idea, it underscores the profound mystery of the cosmos and the possibility that reality might be far more interconnected and more alive than we ever imagined. As we explore the concept of cosmic consciousness, we're reminded that the universe is not just a place of matter and energy, but of meaning and wonder. It's a reminder that our search for understanding is not just about discovering facts, but about uncovering the deeper truths that connect us to the cosmos. And in that search, we might just find that the universe has been conscious all along, not as a distant, abstract force, but as the very ground of our being. This journey into the mysteries of cosmic consciousness leads us to another profound question. What can the ancient light of the cosmic microwave background reveal about the origins of the universe, and perhaps about the nature of reality itself? The answers lie hidden in the faint whispers of the Big Bang, waiting to be uncovered. The universe has a story to tell, and one of its oldest, most profound chapters is written in faint whispers of light that have traveled for over 13 billion years. This light, known as the cosmic microwave background, or CMB, is the afterglow of the Big Bang, a snapshot of the universe when it was just a newborn, barely 380,000 years old. To cosmologists, the CMB is like the universe's first baby picture, offering a glimpse into its earliest moments and providing some of the strongest evidence we have for the Big Bang theory. Imagine the universe in its infancy, a seething, opaque soup of particles and radiation. As it expanded and cooled, electrons and protons combined to form neutral hydrogen atoms, allowing light to travel freely for the first time. This light, once blindingly bright, has stretched and cooled over billions of years, becoming the faint microwave radiation we detect today. The CMB is everywhere, a uniform glow that fills the cosmos, a relic of the universe's fiery birth. But the CMB isn't perfectly smooth. Tiny variations in temperature, known as anisotropies, create a patchwork of hot and cold spots across the sky. These fluctuations, just one part in 100,000, might seem insignificant, but they're the seeds of the universe's large-scale structure. They represent the slight overdensities and underdensities in the early universe regions where gravity would eventually pull matter together, forming galaxies, clusters, and the vast cosmic web we see today. Scientists have spent decades mapping these anisotropies, using instruments like the Wilkinson Microwave Anisotropy Probe and the Planck satellite. These missions have revealed not just the universe's structure, but also its composition: roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The CMB has become a Rosetta Stone for cosmology, decoding the universe's origins and evolution with remarkable precision. What's truly astonishing is how much these tiny temperature variations tell us. They reveal the universe's age, its rate of expansion, and even the amount of dark energy driving it apart. They also provide clues about inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang. The patterns in the CMB suggest that the universe underwent a period of exponential growth, smoothing out its initial irregularities and setting the stage for the cosmos we see today. But the CMB doesn't just answer questions, it raises new ones. Why is the universe so finely tuned? The anisotropies we observe are incredibly precise, their patterns aligning with predictions made by the Big Bang model. But this precision also hints at something deeper, the concept of cosmic fine-tuning. The constants of nature, like the strength of gravity or the mass of an electron, seem perfectly calibrated to allow the existence of stars, planets, and life itself. Is this fine-tuning a coincidence, or does it point to a deeper truth about the universe? Some cosmologists suggest that our universe might be just one of many in a multiverse, each with its own set of physical laws. In this view, fine-tuning isn't a mystery but a consequence of probability. We live in a universe where the conditions are just right because, well, we couldn't exist in one that wasn't. Others propose that the universe's fine-tuning might reflect an underlying order, a set of principles we've yet to fully understand. As we ponder these questions, the CMB reminds us of how much we've learned and how much remains unknown. It's a testament to the power of science to uncover the secrets of the cosmos, one faint whisper at a time. And as we peer into this ancient light, we're not just looking back at the universe's beginnings, we're glimpsing the foundations of everything we know. This journey into the CMB leads us to an even deeper mystery, the concept of cosmic fine-tuning. What does it mean for the universe to be so precisely balanced, and what does it tell us about our place within it? The answers lie not just in the stars, but in the delicate interplay of forces that shape the cosmos, a mystery we'll explore as we continue our journey into the hidden realms of the universe. The universe is a delicate balancing act, a cosmic dance where even the slightest misstep could render life impossible. The strength of gravity, the mass of an electron, the rate of the universe's expansion, these aren't random values. They're precise, finely tuned constants that seem almost tailor-made to allow stars, planets, and ultimately, life to exist. This extraordinary precision has led scientists and philosophers to ask a profound question. Is the universe designed for us, or is this fine-tuning just a lucky roll of the cosmic dice? This idea, known as cosmic fine-tuning, suggests that the fundamental laws and constants of nature are set with such precision that even the tiniest deviation would make the universe unrecognizable and lifeless. Take gravity, for example. If it were just a fraction stronger, stars would burn out too quickly, leaving no time for planets to form or life to evolve. If it were weaker, stars might never ignite at all. Similarly, the mass of the proton and neutron must be just right to allow for the formation of stable atoms. Without these precise values, the universe as we know it wouldn't exist. The anthropic principle offers one way to make sense of this fine-tuning. In its simplest form, it states that the universe must be compatible with the existence of observers because we're here to observe it. It's a bit like saying, we live on Earth because it's the only planet we can live on. But this raises a deeper question. Why does a universe capable of supporting life exist at all? Some physicists argue that fine-tuning might be evidence of a multiverse, a vast collection of universes, each with its own set of physical laws. In this view, our universe is just one of countless others, and we happen to live in one where the conditions are right for life. It's like winning the cosmic lottery. The odds might be astronomically low, but in a multiverse with infinite possibilities, even the rarest outcomes become inevitable. Others see fine-tuning as a sign of something deeper, a hint of purpose or design. Philosophers and theologians have long pondered whether the universe's precision points to a creator or some form of cosmic intelligence. While this idea lies outside the realm of scientific proof, it invites us to consider whether the universe has a story to tell, a narrative that goes beyond the laws of physics. But fine-tuning isn't just a philosophical puzzle, it's a scientific one. Why are the constants of nature so perfectly balanced? Is there a deeper law or principle that explains them, or is fine-tuning simply a fact we must accept without explanation? These questions push the boundaries of our understanding, challenging us to explore not just the how of the universe, but the why. As we grapple with these ideas, we're led to an even more profound mystery, the cosmic endgame. If the universe is finely tuned for life, what does that mean for its ultimate fate? Are we part of a grand cosmic plan, or simply a fleeting spark in an infinite expanse? These questions take us to the edge of science and philosophy, where the boundaries of knowledge blur into the unknown. The concept of cosmic fine-tuning reminds us that the universe is more than just a collection of stars and galaxies. It's a place of exquisite balance and possibility. Whether by chance, design, or some deeper law we've yet to uncover, the fact remains, we live in a universe that seems uniquely suited for life. And as we continue to explore its mysteries, we're not just seeking answers, we're uncovering the profound connections that bind us to the cosmos itself. Now, as we turn our gaze to the cosmic endgame, we're faced with a question that stretches the limits of imagination. What lies at the end of the universe's story? Is it a final, eternal silence, or something even more mysterious? The answers, like the universe itself, are waiting to be discovered. The universe has a beginning, the Big Bang, but what about its end? What happens when the stars burn out, the galaxies drift apart, and time itself seems to stretch into eternity? This isn't just a question for science fiction, it's one of the most profound mysteries in cosmology. The fate of the universe hinges on a delicate interplay of forces, from the relentless pull of gravity to the mysterious push of dark energy. Depending on how these forces play out, the cosmos could end in a dramatic collapse, a slow fade into darkness, or even a catastrophic tear. This is the cosmic endgame, the universe's final act, and it's a story written in the language of physics, time, and space. One of the leading theories about the universe's fate is the Big Freeze, also known as heat death. In this scenario, dark energy continues to push galaxies apart at an ever-increasing rate until the universe becomes a cold, dark, and lonely place. Stars will exhaust their fuel, galaxies will drift so far apart that their light can no longer reach one another, and eventually, even black holes will evaporate through Hawking radiation. The universe will reach a state of maximum entropy where no energy is left to do work and all motion ceases. It's a quiet, almost poetic end, a cosmic sigh as the universe fades into eternal stillness. But what if dark energy doesn't have the final say? Another possibility is the Big Crunch, a dramatic reversal of the universe's expansion. If dark energy weakens over time, gravity could eventually take over, pulling everything back together in a cosmic collapse. Galaxies would rush toward one another, temperatures would soar, and the universe would shrink back into an infinitely dense point, a mirror image of the Big Bang. Some cosmologists speculate that this could trigger a new Big Bang, birthing a new universe in an endless cycle of expansion and contraction. It's a cyclical vision of the cosmos where endings are also beginnings. Then there's the Big Rip, the most violent of the possible fates. If dark energy grows stronger over time, it could overcome not just the pull of gravity between galaxies, but even the forces holding atoms together. In this scenario, the universe wouldn't just expand, it would tear apart. Galaxies, stars, planets, and eventually even molecules and atoms would be ripped to shreds, leaving behind a universe of isolated particles drifting in an endless void. It's a cosmic apocalypse, a final, catastrophic unraveling of the fabric of reality. These scenarios might sound like the stuff of nightmares, but they're grounded in the latest observations and theories. The key player in all of this is dark energy, the mysterious force driving the universe's accelerated expansion. Depending on how dark energy behaves, whether it remains constant, weakens, or grows stronger, the cosmos could face any of these fates. Right now, the evidence points toward a big freeze, but the universe is full of surprises, and cosmologists are constantly refining their models to account for new discoveries. Amid these dramatic possibilities, it's worth reflecting on humanity's place in the cosmic story. We've come so far from staring up at the night sky in wonder to mapping the large-scale structure of the universe and probing the mysteries of dark energy. Yet, in the grand sweep of cosmic time, our existence is but a fleeting moment. The stars we see today will one day fade, the galaxies we study will drift apart, and the universe itself will continue to evolve long after we're gone. But this isn't a cause for despair, it's a reminder of the extraordinary privilege of being here, right now, to witness and understand the cosmos. In the face of the universe's vastness and its uncertain future, we find meaning not in permanence, but in the act of exploration itself. Every discovery, every question, every moment of awe connects us to the grand narrative of the cosmos, a story that began with the Big Bang and will continue long after we're gone. As we ponder the universe's final act, we're reminded that the journey is as important as the destination. And in that journey, we find not just answers, but a deeper connection to the cosmos and to each other. The universe's fate may be uncertain, but our role in its story is clear: to explore, to wonder, and to marvel at the beauty of it all. This reflection on the cosmic endgame leads us to an even deeper question. What does it mean to exist in a universe that's both vast and fleeting? As we continue our journey, we'll explore how humanity's search for meaning intersects with the mysteries of the cosmos, weaving together science, philosophy, and the timeless quest to understand our place in the universe. We are the universe made conscious, a collection of stardust that has learned to look up and wonder. Every atom in our bodies was forged in the hearts of ancient stars, scattered across the cosmos in supernova explosions, and eventually gathered here on Earth to form the building blocks of life. From these humble beginnings, humanity has risen to become a species that not only observes the stars but dreams of reaching them. Our journey from stardust to stars is a testament to the extraordinary potential of life in a vast, seemingly indifferent universe. The story of human exploration is one of relentless curiosity and audacious ambition. From the first steps on the Moon to the rovers exploring the dusty plains of Mars, we've pushed the boundaries of what's possible. Spacecraft like Voyager have ventured beyond our solar system, carrying messages to potential extraterrestrial civilizations, while the Hubble Space Telescope has revealed the breathtaking beauty of galaxies billions of light-years away. These achievements aren't just technological triumphs, they're milestones in our cosmic journey, reminders of our capacity to reach beyond our limits and touch the infinite. Yet, as we celebrate these accomplishments, we're also confronted with profound challenges. Space exploration is fraught with obstacles, from the physical dangers of radiation and microgravity to the ethical dilemmas of planetary protection and resource exploitation. How do we balance our drive to explore with the need to preserve the environments we encounter? What responsibilities do we carry as we venture into the unknown? These questions aren't just scientific, they're deeply human, forcing us to reflect on the kind of legacy we want to leave in the cosmos. Scientists and visionaries have long pondered our role in the universe's story. Carl Sagan once described Earth as a pale blue dot, a fragile oasis in the vastness of space, urging us to cherish and protect it. Stephen Hawking believed that humanity's survival depends on becoming a multiplanetary species, spreading life beyond our home planet. And today, thinkers like Elon Musk and organizations like NASA are working to make that vision a reality, developing technologies that could one day take us to Mars and beyond. But what does it mean to be a spacefaring civilization? Is it about conquering new worlds, or is it about understanding our place in the cosmos? Perhaps it's both, a journey of discovery that expands not just our horizons, but our sense of connection to the universe. Every time we launch a rocket, every time we peer into the depths of space, we're not just exploring the cosmos, we're exploring ourselves, uncovering the threads that bind us to the stars. As we look to the future, we're faced with a question that transcends science and technology. What legacy will we leave in the cosmos? Will we be remembered as explorers who ventured into the unknown, or as a species that squandered its potential? The answer lies not in the stars, but in the choices we make today, as individuals, as societies, and as a global community. This journey through the hidden realms of the cosmos has taken us from the mysteries of dark matter and dark energy to the breathtaking possibilities of wormholes and multiverses. We've explored the birth of stars, the death of galaxies, and the profound questions about time, consciousness, and existence itself. Each discovery, each insight, reminds us that the universe is far more vast, more beautiful, and more mysterious than we ever imagined. But the story doesn't end here. The cosmos is an ever-unfolding narrative, and we are both its audience and its authors. As we continue to explore, to question, and to dream, we're not just uncovering the secrets of the universe, we're adding our own chapter to its story. And in that story, we find not just answers, but a deeper connection to the cosmos and to each other. So, as we stand on the precipice of a new era of exploration, let's remember that the journey is as important as the destination. Whether we're gazing at the stars or stepping onto new worlds, we're part of something greater, a cosmic journey that began with stardust and will continue long after we're gone. And in that journey, we find not just wonder, but meaning, a reminder that we are, and always will be, the universe made conscious. From the invisible scaffolding of dark matter to the mind-bending possibilities of multiverses, the hidden realms of the cosmos have taken us on a journey that stretches the limits of imagination. We've peered into the hearts of black holes, marveled at the delicate cosmic web that binds galaxies together, and pondered the profound mysteries of time, consciousness, and the universe's ultimate fate. Each step of this exploration has revealed a cosmos far stranger, more intricate, and more awe-inspiring than we ever could have imagined. These ideas aren't just scientific curiosities, they're invitations to rethink our place in the universe. We've seen how the smallest particles are connected to the largest structures, how the birth of stars echoes the birth of the universe itself, and how the questions we ask about the cosmos often lead us back to questions about ourselves. Whether it's the enigma of dark energy driving the universe's expansion or the tantalizing idea that the universe might be conscious, these concepts challenge us to see reality not as a fixed set of rules, but as a dynamic, evolving story, one that we are both part of and shaping. As we reflect on these mind-expanding perspectives, one thing becomes clear: the cosmos is a realm of endless mystery and wonder. It's a place where the known and the unknown coexist, where every discovery opens the door to new questions, and where the boundaries between science, philosophy, and imagination blur. This journey isn't about finding all the answers, it's about embracing the beauty of the questions themselves, about finding wonder in the unknown and meaning in the search. Carl Sagan once said, "We are a way for the cosmos to know itself." In these words, we find a profound truth that our curiosity, our desire to explore and understand, is not just a human trait, it's a cosmic one. Through us, the universe becomes aware of its own existence, reflecting on its origins, its structure, and its future. And in that reflection, we find not just knowledge but connection, a deep, resonant bond with the cosmos that reminds us how extraordinary it is to be alive in this vast, unfolding story. But the journey doesn't end here. The universe is full of mysteries waiting to be uncovered, and each of us has a role to play in that discovery. Whether it's through stargazing, reading about the latest scientific breakthroughs, or simply pondering the big questions, we can all be explorers in our own way. So, what do you think about these cosmic mysteries? Which ideas sparked your curiosity the most? Share your thoughts in the comments below. I'd love to hear your perspective and continue this conversation together. If you've enjoyed this journey into the hidden realms of the cosmos, don't forget to subscribe and hit the notification bell for more mind-expanding explorations. Together, we'll keep unraveling the universe's greatest mysteries, one discovery at a time. Until then, keep looking up, keep wondering, and remember, the cosmos is not just out there, it's within us, a story we're all a part of. As we close this chapter, let's carry with us a sense of awe and curiosity, a reminder that the universe is not just something we observe, but something we're deeply woven into. The journey of discovery is never ending, and the cosmos will always have more secrets to share. So, let's keep exploring, keep questioning, and keep marveling at the infinite possibilities that lie ahead. After all, as Sagan so beautifully put it, somewhere, something incredible is waiting.